I've drawn 3 circles here. And I actually tried to draw 3 really good circles here. In fact, I went through all the trouble of tracing my coffee tin lid, a lid off of ginger from the pantry, and a dime that was in my pocket. And I'm a little disappointed that I only drew okay circles. But they'll still help me talk about curvature. I want you to look at the 3 points I've plotted. And I want you to look just closely around those points on those circles. And I want you to assign one of those circles as having the most curvature, whatever that means, and one of them is having the least amount of curvature. Just looking around those points and thinking about curvature as a rate of turning. If you're traveling around those circles, right, they bend, one of them is bending the fastest. Pause the video here and see if you can pick out which one has the most curvature. So I'm hoping that you thought this one had the highest amount of curvature. Looking just near that point, it looks like this circle's turning pretty quickly. It's very curvy. And then this one has the least amount of curvature. In fact, if you just look really, really close to that point, it actually looks fairly straight. So I'm going to say this has the smallest amount of curvature, and this has the most. And then this one's just stuck in the middle, and I don't have a lot to say about it. All right, so let's see if we can rigorously define curvature. I want to imagine that I have a smooth curve in space parameterized by a vector function r. So I have some curve in space, and when I say smooth, we mean that I can take derivatives at every point, so no sharp corners, and it is continuous at every point, so no hop, skips, breaks, or jumps. And this is obviously curving in a couple places, actually in all of the places, and I put a dot here because that curvature reminds me of one of the smaller circles, and this curvature reminds me of one of the largest. And so we actually define curvature by looking at what our unit tangent vector is doing as it moves with respect to unit length. Things that are really curvy, like my small circle, that unit tangent vector moves very quickly. Where my curve is flatter, my unit tangent vector will turn less quickly. And so to define curvature, we actually look at the derivative of that unit tangent vector with respect to unit arc length. The magnitude of dt ds, the rate of change of the unit tangent vector with respect to unit length. And we denote curvature using the lowercase Greek kappa, which doesn't actually look like that, but it's the best I can do. So there's my definition of curvature, and I hope that it will agree with my thoughts about curvature here. That when I finally get to calculate curvature, big circles will have small curvature and smaller circles will have large curvature. And then I can measure how curvy something is for any smooth function r. Well, this is a great definition formula, but it's not a great calculation formula. I could reparameterize a function in terms of the arc length parameter, right? Substitute t equals in it after I've solved the arc length parameter for t if I can, and then take a derivative and have velocity, and then calculate big T, and then take its derivative with respect to s. But that might not be very convenient, and it's not always even easy or possible to solve the arc length parameter for t. So the better calculation formula comes from the chain rule. This derivative, because of the chain rule, is the same as the derivative of big T with respect to t times dt ds. All right, well, that dt ds is a scalar function. So it can pop out of my magnitude bars and be in just regular absolute value bars. And I recognize dt ds as the reciprocal of ds dt, which is speed. So this formula boils down to 1 over speed times dt dt. And this is great because everything in this final calculation formula is is in terms of the original variable t. So this is how I'll calculate curvature. Kappa is equal to 1 over speed dt dt. So let's take a look at a circle. So if I have a circle, r of t equals a cosine t, comma a sine t. I'm thinking space curve here, but I'm just going to let z be 0. So I'm in the xy plane. And I could actually just omit that. But r of t is a cosine t, comma a sine t, parametric equations of a circle. I want to calculate curvature, which means I need to know speed, big T, and the derivative of big T. So let's start with the derivative. It's also worth noting that the circle I started with here is a circle of radius a. All right, so I've found velocity. Let's find speed. And I'm skipping a step here. A squared sine squared t plus a squared cosine squared t. Go on and factor out an a squared. Good old Pythagorean identity there tells me that this is just a. All right, so the speed is a constant around this parameterization of a circle. That lets us write down big T. And of course this is a unit vector, right, with that sine and that cosine respectively. We could think about that. And so now I'm ready to actually calculate curvature. I need to know the derivative of big T with respect to T. And its magnitude. Well, it's pretty easy to tell that that vector has a length of 1. So now I'm ready to calculate the curvature for this circle. Kappa equals 1 over speed times dt dt in magnitude. For a circle, the curvature is 1 over the radius. Well, we wanted this to match what we said initially. Well, this circle has a very small radius, and if I take the reciprocal of a small number, I get a big number. This circle has a very large radius, or at least by comparison, I take the reciprocal of a large number and I get a smaller number. So the idea that a reciprocal to the radius gives the curvature of a circle makes sense. Okay, well that's it for now.